Good morning.
Morning.
I'm going to be talking about the mill CPU and its architecture and the intersection with LLVM as a progress report reflecting how far we've gotten in the process of retargeting LLVM for the mill architecture. In order to do this, I need to have a sense of what is the level of prior experience with the mill. Who has never heard of the mill before seeing it on the program? Oh boy. Okay, well, for those of you who are newbies, you'll find a vast quantity of material on the details of the architecture on our website. The URL will come up on a later slide. There have been essentially no major advances in architecture for the last 30 years, not since the introduction of caches. The machine, which is in your laptop, is recognizably similar to a 36091 vintage 1970s. And the reason why there has been no, despite the fact that there's been immense advances in circuit design, in fabrication, even in compiler technology, the reason why there has been no advance is entirely a matter of network effects. Certain markets were captured, and then legacy needs wound up governing everything. Most vendors know how to do better architectures today, but they had no economic incentive to actually introduce such a thing. And the few cases where they did attempt to do so, the Itanium being the glaring example, fell into hard times and difficulties for a variety of mostly non-technical reasons. The mill is a clean thing, a clean slate rethink of the of what it means to be a general purpose CPU. It is not a special purpose CPU. It is intended to go into your cell phones, your laptops, your friendly local supercomputer, and anything else you can think of, especially focused on single thread performance, power, and in particular, the kind of control flow heavy codes which are typical of general purpose codes as opposed to the multiply, accumulate banging that is typical of a GPU. Yes, you can multi-core a mill. You'll have the same advantages and drawbacks that you have multi-coring anybody, and we look forward to the software solutions that will take an arbitrary piece of code and break it up into pieces for multiple cores. That'll work for us too, but frankly, we're somewhat doubtful about the reports that this is being successful. This is one of a series of talks describing the machine. The mill is fundamentally very, very different than a conventional machine, and you'll be able to find far more than you want in technical detail at that URL. It is a family, like a 360 is a family, quite wide range. We have a 10x power performance advantage over conventional machines, such as you find in your present laptop, and I'm prepared to justify that number, but offline we will get sadly distracted if people start asking me questions about that kind of thing. And we'll touch on why the mill tool chain is different, and it's rather different than most, although I did see some talks today which were appeared to be addressing similar issues. We have a target independent assembler and a target dependent assembler. How the targets are specified for across the family members. I'll touch on a few things about the mill architecture that are required to understand the rest of it. There is vastly more. And then we'll end with a progress report on our experience with LLVM to date. The instruction set architecture, which is the target. It is a wide issue machine. The high end can issue up to 30 operations sustained every cycle. These are independent MIMD operations, adds, multiplies, shifts, what have you. Think of a 30-wide VLIW. The mill is not a VLIW, but with respect to instruction issue, it is in fact rather similar to a VLIW, except an exceptionally wide one. It is statically scheduled. Consequently, there's no issue hazards. It has an exposed pipeline, all operations, gentlemen. Go on up, there's no... the operations have a statically known fixed latency. Vectors are integrated. Every scalar op is a vector op as well, and the data carries metadata information that says the width which is involved. The data, if there's one add operation that covers all possible adds, and there's no distinction, add, byte, add, half word, add word, and so forth. And you can get more info there. Okay, I'm not sure how we succeeded in getting out of that, but we did. Are we back up? Yes, we are back up. Let's hope that does not happen on a regular basis. What is in fact most unusual is that there are no general registers at all, and the hardware is static single assignment. Consequently, when you are, we cannot use the standard LLVM backend, which converts everything to a linear form and assumes the presence of registers. The talk is a gross oversimplification. Those of you who know how things work on the inside of a CPU will know that I am lying through my teeth, but as a practical matter, especially for an audience unfamiliar, I have to simplify it. The details are available. Feel free offline to ask me absolutely anything. I love to brag about the baby, and you'll get all the details you want. I keep getting back to that. No? Does anyone? No. I think what it is, oh, I see, there's an end button, I got it, and I'm hitting that too. Okay, my apologies, folks. I will attempt to avoid hitting the wrong button. To give you an illustration, I think perhaps sitting down might solve some of this problem. To give you an illustration of how things are different, as seen by the compiler, your normal semantic model which your program addresses has got a stream of instructions, individual instructions. That is a physical model. In reality, a modern machine has to do multiple issue and execute multiple instructions simultaneously, so the actual model involves bundling instructions into multiple execute units. If those instructions are of fixed length, then they are extremely easy to figure out where the boundaries of a bundle are and drop each of the instructions into decode. Unfortunately, in order to accommodate all possible instruction sizes, your single instruction fixed length width has to be very large. The Itanium, it's 41 bits. And 30 times 41 bits is going to plug up your entire instruction cache pathway and is impractical in real hardware. The alternative, of course, is you use variable length instructions. The difficulty with this is that where does the next one start? Parsing from the front is problematic, shall we say, because in order to determine on a linear parse, you have a polynomial cost in that parse. And despite true, incredibly admirable heroics, the Intel people are able to parse 4 instructions out of their instruction stream, but 30 is totally hopeless. However, if you have two bundles of length n, because it's polynomial, why, that's much, much easier than one bundle of length 2n. So if you split each bundle in half and have two streams of half bundles, then you're taking advantage of the polynomial, and you are going to be able to parse twice as many instructions at whatever limit. If the Intel folks were to use the same trick, they might be able to parse 8 instructions doing 2 streams of 4 instructions each. Now, this of course means that you have to have 2 program counters, and that you have 2 physical streams, but there's only one logical stream. You've just broken an instruction bundle in half into 2 pieces. Question, of course, is how do you branch 2 streams? With 2 program counters, you need two program offsets in your branch operations, or 2 pointers in if you're doing indirections for calls, for example. And our solution was we broke all of the code into extended basic blocks. This is single entry, multiple exit, and in our case can contain embedded calls, but that's not a matter here. So each one of these instruction streams actually is a chain of EBVs with the program counter pointing into one and branches connecting to the beginning of another EBV. You cannot branch into the middle of an EBV, only into its head. Well, once you've done that, if you take 2 half EBVs where you've got the head of each, and they are executed in order as shown in the arrow from lower addresses to higher addresses. Now, if you reverse one of these in memory, note that the 2 halves of the same instruction are the same color, so the 2 yellows there are the 2 halves of one instruction. You reverse it in memory, and then join them head to head. You have an entry point like that. Now, when I want to do a branch, the effective address is there. It's going to the heads of the 2 half EBVs. And guess what? The 2 heads are at the same address. So I only need 1 offset in my branch operation. Now, as I execute, we start after the branch, both program counters point to that entry point. And we still have 2 decoders because we're decoding 2 operation streams. And those decoders are, of course, feeding all the execute engine. So we peel off the 2 half bundles, drop them into decode into execute, and advance the program counter to the next half bundle going away from each other. So one stream is decoded toward higher addresses, and the other is decoded toward lower addresses. It's a great deal of fun to say to people that we have 2 instruction streams, the 2 program counters, one of which runs backwards. And exactly what it means to run backwards, well, you're seeing, and they will step through bundle by bundle. Now, this obviously takes advantage of the polynomial aspect of variable length decoding, but it has an additional advantage. One of the constraints in real CPUs is you can never have enough instruction cache. This is especially true if you have very wide operations. But the problem with instruction cache, you could put as much instruction cache on the machine as you want, but the problem is that the bigger the instruction cache, the further away the far end of the instruction cache is from decode. There is a critical distance measured in wires that is from the far side of the instruction cache to the decoder, and that determines what your fetch rate is going to be and what the your branch miss penalty is going to be, and a number of other factors. So that distance is architecturally critical at the circuit level. Now, I could increase the I-cache, but when I do that, my critical distance is also increased, and the penalty, well, there's always a trade-off between wanting more instruction cache and wanting faster machine, and it's not nice to have to choose. So in a mill, you don't do that. Instead, because there are two instruction streams, you have two instruction caches and two decoders. As a result, we now have two critical distances, and we have the speed of a conventional, but with twice the cache capacity. Now, think about generating code for a machine in which a wide instruction is split and decoded in both directions. That is part of the task of our toolchain. I've just given you this as an illustration. This is far from the strangest thing about the mill. By all means, go and explore. You'll have fun. Now, it's a family. The families share an abstract operation set, and they share a common microarchitecture. However, those family members, these four are our proof of principle preliminary implementations that we're working on. They differ in the concrete operations set. Tin has no floating point units. They differ in the details of the microarchitecture. The length of the facilities that you store temporary variables on differs from family member to family member. You define a particular family member by writing a specification. That specification is 2 to 3 pages of C++, and you can make a change in that and recompile it and turn the crank, and 15 minutes later you have a new assembler for this new member, a simulator that simulates it, the things that the hardware guys use to generate the Verilog for the real hardware, online documentation, and what have you. It's all mechanically specified. Nowhere have we just said, this bit means this, and this bit means this, and this bit means this. As you'll see later, LLVM really does not like this. And it's ironic because as a result of the specification, the mill's instruction set is extraordinarily regular. There are no odd peculiarities where an engineer was able to save a gate by making some special case of one particular operation that the compiler has to deal with. Everything is regular, and as usual, no good deed goes unpunished, and we discovered that LLVM actually doesn't really like being given an extremely large operation set that is extremely regular. Those family members, when we create the system software, produce tool sets. That's all mechanically driven off the data in the specification. Why use a family? CPU hardware, semiconductor, is like cement plants and steel mills and railroads. It's fabulously expensive and takes an incredible long time. We are a bootstrap startup. We've been at this for 12 years already. We still do not have something we can sell you. Soon, we hope. But it is phenomenally expensive. If you are Intel or IBM and can put 300 people on this task, well, it still takes a fairly long time, and it takes a whole lot more money, but fundamentally, we're not going to be able to anticipate what is going to be the chip in demand far enough in advance. As usual, business questions often influence technical answers, and that's certainly true here. We can't guess what what it will be the hot chip market in 2017. We couldn't have guessed that 10 years ago, and we didn't want to bet the company on making a guess. So instead, our solution was re-architected the design with a broad appeal for many, many markets, general purpose. those individual chips can be tuned for particular markets, which meant that there needed a binary compatibility across the family. I'm not talking x86 style binary compatibility where you still wind up having to specify the particular target machine or you run like a 386. We're talking true binary compatibility throughout. The specification is the reason why the specification is used is because doing it by hand is fabulously expensive, and much of that process is repetitive, very easy to get wrong accidentally, incredibly boring and wasteful. In addition, things often wind up being suboptimal because basically the engineers run out of patience and capacity to think about it anymore. I don't want to do is ship the thing. When you're working on a specification, you'll see on our website the detailed bit-level definition of the operation set as of today. And you'll discover that the website changes in 3 days because we've added a new operation and all the bit patterns have changed because it's all done mechanically. We knew we lacked the resources, so we got the software to do it. The result, we can address multiple markets efficiently. We can pivot fast to a new chip if a new market opens up. And it's economical for us who have to do the work and for our future customers. Now, how do you do a family? Traditionally, you use microcode. That's what the 360 did. And the 360 is thriving today. They don't call it the 360 anymore, but it is still there, and that architecture is still in use. And the reason why they were able to do it is because they hid the real machine down behind a microcode level. You can hide the functional unit population by using superscalar or out-of-order techniques. However, both microcode and superscalar out-of-order have extremely high runtime power performance costs. A hardwired static, such as you'll find in the DSP, easily gets a 10x power performance advantage over the kinds of things that you are seeing inside your laptop. Those of you who ever worked with DSPs, if you have a compatible fab, know that 10x is readily available. The problem is that DSP code, DSPs are not able to run general purpose code. So we wanted to get a hardwired power performance and the binary compatibility. And of course, the simple solution is late binding. That deserves a little bit of an exclamation mark. So we do late binding to the family members. We compile to the abstract target. This is the generic mill which has got infinite resources. It's a universal superset. We take our C++, run it through your friend and mine, through the LLVM middle end, to the LLVM backend? Well, no. The LLVM backend makes gross assumptions about the nature of a computer, and we don't work like that at all. So instead, we pull out just at the end of the middle end or the front of the back end. We actually wound up needing to get a couple of the back end passes brought into but we do, so those actually wind up being glued onto the middle end. And the result is an internal format which retains static single assignment and data flow. It has not been registerized. It has not been turned into bitcode. It looks very much like the LLVM middle pass IR and suitably modified to carry additional information that we use later on, as you'll see. Now, in order to test this thing, we needed to have a way of getting in without going through the LLVM thing, because our port for the LLVM doesn't work yet. And, well, it actually does somewhat work, but only in limited cases. So we wanted to have a assembler level interface using the GenAsm language, which has an assembler. And GenAsm is actually a data flow language. It does not look like assembler at all. You are writing data flow. It is as at the source level, it is single assignment. And the GenAsm assembler will produce the same gen form that the LLVM toolchain produces. And that goes into a link step. Then, from that link stuff, we specialize to the concrete target. Everything that you see on the slide at this point does not know what the target machine has. It doesn't know if it has floating point. It does not know how many ALUs it has. It does not know what the concrete target is. So at the point where we do know what it is, we've got the executing family member, and the tool there is called the specializer. You can think of it as being a freestanding backend, taking in gen form, and our target specification, the same thing that tells everybody else what the target is, and the specializer produces conform, which is our bit code and is actually what the loader will load into memory. Naturally enough, we need an assembler that works at that level too, and the language that it accepts is ConAsm, and the ConAssembler goes to conform, and conform goes to, guess what, another link step. And that in turn ultimately will wind up at the loader in the CPU. This is our tool chain. And the reason for doing this is that the individual family members are not bit-level binary compatible. But with this, they are load module compatible, and it's the load module compatibility that the users actually care about. ConAsm language you might find a bit interesting. The concrete assembly syntax is actually C++, suitably disguised. The traditional assembler's got two passes. It takes the first pass typically is a macro pass, and then that produces a separate program, which is then actually assembled to the binary level to produce a machine language output. So your source file in the macro language, first pass goes to machine language, second pass translates it into the machine form. Classic assembler. We're not talking the assembler that is glued onto the back end of a C compiler. I'm talking about a real assembler. Those of you who are sufficiently antique, such as myself, may actually know what I'm talking about. Most people these days actually have never used a macro assembler, but with a good macro assembler, you can brush your teeth. You can do wonderful things with it. Our first pass is actually C++. The assembly language source program is actually C++. We take the source file, which is written in C++, although it looks like assembler, feed it through the C++ compiler, gets us a program. We run the program, and executing that program is the second pass, and the result of that execution is the binary. How that works? Each assembler operation is actually a C++ function call. If your conventional assembler says add a B3 and B5, those are belt numbers. Any of you who have seen any of our stuff about a belt, we won't sidetrack into that, but I'm again open for questions later. The mill assembler looks like that. And it is in fact a C++ function call. You say jump, that's mill assembler, ConAsm, not GenAsm. Note that we had to mangle the syntax a little bit to get C++ to accept it. A mill instruction, remember we have multiple operations, is a C++ statement. The whole thing, including all the commas. How many people are aware that the comma operator is an overloadable operator in C++? more C++ expertise than I might have expected. That's, many people are just totally boggled by the concept. And what we've done is we've used that so that the comma operator delimits the operations and the semicolon delimits the instruction. This is the only time I've ever seen an actual useful use of overloading the comma operator. Okay? Now, because we're in C++, every call of one of those ASM functions emits the corresponding operation. So if I write something like that, you'll get the same resulting machine code as that, because we're using C++ as a macro meta language. You can use your C++ code to build complicated data structures and have it emit the results as you see. You write your meta program to produce the machine program that you have in mind, and this is exactly what you do in a classic macro assembly. By using C++, we were able to save the cost of having to produce our own macro assembler. In order to get C++ to do all of this, well, it's an H file with the declarations for required to make it eat this thing, and then, of course, all the backend that produces the binary that we would have to have done anyway. Now, how do we do the specification? It's done by attributes. The operation comprises, each operation comprises a core operation and the values for attributes. Thus, if that is one of our operations, the ADDUS is, of course, is the mnemonic, and B3 is the value from the belt. Think register 3, and 17 is a literal. The core operation here is add. So the attribute is that in addition to the core operation, one of those attributes is the domain. And the domain there is indicated by the character U, which says this is in the domain of unsigned integers. Then every operation that can overflow on the mill supports 4 possibilities. We can ignore the overflow. Yes, well, most compilers do. We can do saturating arithmetic, which is common in much embedded work. We can give you something that sooner or later will give you a hardware fault, and we can give you a double width result that cannot overflow. In this particular case, the S there says that this operation is doing saturated arithmetic. Remember how I said everything was exceptionally regular? All those 4 possibilities exist for every operation that can possibly overflow on a mill. Then we have an operand, says the third belt position, and an immediate value is a literal. This is the mechanism for how the assembler operations are built. For each operation, when we define a machine, we list all possible attributes that are meaningful for a particular core operation. What can you do within the core notion of an add? Well, I can add floats, and I can assign integers, and I can add unsigned integers, and guess what? We have both binary float and decimal float. These are all domains, and so on, so that what the software does, given the specification, oh, you can overflow, will produce the cross product of all the meaningful attributes as separate operations, and then figure out the optimal entropy bit pattern for expressing all of those operations on each different machine with the actual functional unit population that that particular family member has. It may be supplied by operation mnemonic or by argument. There are roughly 50 attributes, but typically only a handful, 5 or 8 or something like that, are meaningful for any particular operation. Thus, you don't care whether it's branch true, branch false for an add, but the branch operations certainly care if it's branch true, branch false. Those values, most of them are enumerations, direction codes for shifts, conditional senses for branches, overflow code I've already mentioned, domains. Specification specifies the attributes individually or as power sets of what is permitted or meaningful. The mnemonics are mechanically generated. Each one of those attributes has a nick so that we simply concatenate all the nicks to produce a appropriate mnemonic and generate an assembly that recognizes those. The specification, for example, shift RS there, it's a shift right signed. Nobody did that by hand. That's all done mechanically. There are about 120 core ops and well over 1,000 individual operations. I'll skip this because I think you want to spend most of the rest of the time on LLVM itself. The British amongst the audience may recognize that quote. It's from The Hunting of the Snark, and I personally have not been involved in the guts of the LLVM effort. My background is compilers. The first compiler I ever wrote was for a commercial mainframe that is still being sold, and 45 years later, that compiler is still in use. So I know compilers, but I don't know LLVM. And if you start asking me about, oh, this function and this function and this function inside LLVM, I'm going to say, I'm sorry, I don't know. What I can do, however, if you want that level of detail about anything I'm reporting here, because I'm reporting the experiences of our compiler team, and I can put you directly in touch with the real people who've been doing the real work if you want any of the details behind any of this. I'm sorry that I cannot do it personally. The issues. This one is the biggie. The mill pointer it's a 64-bit machine, but pointers are not integers. They have special semantics. The address portion of a pointer is 60 bits long, and the private bit there is used to support the fork operation in Unix and determines whether the addresses are absolute or relative to your process. The barrier mask bits are used to support simultaneous garbage collection and speed up the garbage collection garbage collectors by something in the vicinity of 25%, because it is no longer necessary to check whether a particular pointer has already been looked at or not, because the hardware does that for you. Those bits to us are important, but it does mean that we have separate ops for pointer arithmetic. Add P means add a value to a pointer and verifies that we don't overflow into those 4 bits. And this is not the same as an integer add. That distinction well, it determines what the address is going to be for the private pointer. It's like position-independent code only for data. We can do a copy for a fork, but retain referential integrity. Unfortunately, LLVM loses pointerhood. Furthermore, it loses pointerhood all over everywhere. In particular, it loses the back end, but we are fortunate that we don't especially care because we're doing our own back end. But various passes generate pointer to int conversions and lose the fact that this was actually a pointer. The optimizers in a number of cases say, oh, well, we're going to optimize a constant propagation or a bunch of other things, and they simply turn the thing into being an int and use the existing int optimization, and unfortunately never redecorate the thing with pointerhood. It turns out, to our great surprise, that there are even such problems inside the front end. Again, I'll be happy to put you in touch with the guy who can show you where it is, but the result is that we can't use LLVM for garbage collected languages, and we can't use it for Unix because Unix requires fork. Apparently, others have had the same problem, only not as bad. We just fell over it completely. The individual problems appear to be too pervasive for us to fix. We're a tiny startup, and we can make the changes that we need, but fixes which have repercussions throughout the LLVM trunk are well beyond us. So we look to the community to rediscover what it was really a pointer that got lost. One of the things that you might do is start with checking for pointer preservation in any new code being checked in. That at least will keep the problem from getting any worse. This was by far the biggest single issue that we've encountered. The machine maintains width tags. A add byte operation is not any different than an add word operation or an add double operation. They are exactly the same binary opcode because all the data during execution carries metadata tags that indicate the width. Not only does it indicate the actual width, is it a byte, a half, a word, or what have you, but it also says whether it's a scalar or a vector. This is maintained by the hardware, and consequently the opcodes do not say what width they are expecting. They are polymorphic across all possible widths on the machine. We do have requirements. For example, add requires that both operands be of the same width, but even that restriction is relaxed for some cases. For example, the shift operations do not require that they be the same width. The result will in fact have the width of the left-hand operand, but the right-hand operand, which is the shift count, will accept anything at all in the hardware. When you do a load operation from memory, you specify what width you're going to load. So there is a difference, load byte, load half, what have you, but none once you get the value up into the memory. The single add there works for all of these. That's the same actual binary bit pattern in that instruction stream that I showed you at the very beginning. Unused bits are not driven. This is not type information, it is width information. A 4-byte int has got exactly the same tag as a 4-byte float. We looked into having type information, but it turns out that it's impossible to regularize types across all the kinds of languages which we in hardware need to support, so we reduced ourselves to width. If you want to change from integer to float, that's explicit code that has to do that. Up to the compiler to keep track of it. Guess what? If the C++ does a reinterpret cast from integer to float, from integer to pointer, we need actually to be able to check that operation to verify that it's not being given something with the funny bits turned on. So there again, we hit the pointer problem in maintaining type. We thought that, because of the width tagging, that code generation and instruction selection would be easy, because you didn't have to deal with the fact that certain widths are not supported on the machine. This is especially a problem with vector operations. Any of you who are trying to generate code for vector operations as they are currently being done knows what a pain it is, because every single version of the machines have got a different vector set. And we expected all of that would go away, because everything is uniform. We wish it was true. It turns out, in fact, that that statement is false in LLVM. Well, we tried to replicate the target description for all ops for all 10 possible widths. Welcome to TableGen. TableGen is not designed for our kind of a machine. It's not clear that it's designed for any kind of machine, but that's a different issue. Our solution ultimately was brute force. We replicated the target description 10 ways. It works, but I'll return to table gen later. The mill handles variatic and multiadic operations. For example, an FMA, everybody knows, X times A times B plus C. But in our case, we pair encoding slots so two floating point units adjacent to each other can exchange operands. The belt has got values that go in. Those two slots will independently do a multiply and then exchange the result of the multiply, and one of them does an add and the other does a subtract. So the fuse, multiply, add, subtract operation computes sum and difference of two products. This is rather useful for people doing complex arithmetic, but most importantly, it's essentially coming for free because the hardware's already there to do the multiplies and the adds. All you had to do is make it available. Getting LLVM to recognize this in instruction selection turned out to be more difficult than we expected, and so for now we're only reaching it via an intrinsic. We have hope that with a little bit more work we will be able to recognize that this thing over here, the sum of two products, and this thing over here, the difference of two products, is in fact combinable into a single operation, but we have not gotten that working yet. Function calls. Mill functions are very, very different than a conventional. The belt holds your intermediate operations. Think of them as being your register set, except that it's a queue. The operations give you source operands, but no destination operands. Instead, the results of a computation are implicitly dropped on the front of the queue, pushing all the values of the queue along, and the ones at the end drop off and disappear completely. This is how the mill is single assignment. There are no registers to update. There's no write after write hazards or read write hazards at all. You simply cannot overwrite a value in the belt. You add new values to the belt. So let's say that that is our initial belt value, and that is our call operation. No, you don't, there's not an idiom for call where you diddle the operation pointer and the frame pointer and the this and the that and save all the registers yourself. No, none of that. There's one operation which takes a function and an argument list. That's all you have. It's the only way to do a call in the hardware. In this case, we're calling the function and passing it 4 arguments, which are the values in the first, fifth, third, and third in the caller's belt. That dotted line means a cycle boundary, and 1 cycle later you're now in the callee, and he starts off with an empty belt, no contents at all. But the hardware drops into that belt the arguments. So when you start in a new called function, all of the what would be registers in a conventional machine, not only are they cleared, but in fact they don't even exist, because if you attempt to reference one of those, it'll fall. Some cycles later, let's say that this is now our belt at the point where we do a return operation. A cycle later, we're back in the caller, and you note that we have restored the caller's belt. This is entirely done mechanically by the hardware, and with one slight addition, that the result is dropped onto the front of the belt, pushing the belt along and dropping a value off the back. In this, call works exactly like add. It takes some arguments, it does a computation, and it drops the result on the front. Well, that is fine, except for the fact that the call operation can drop multiple results. They're not restricted to just one. You can drop 6 if you want. There's quite a few languages which really like that capability, C not among them. The automatic save restore, the caller sees all registers as if they were callee saved, but the callee sees all registers as if they were callers saved. Can they save both, but neither? Fortunately, we leave LLVM before we have to address the problem of saying which things get saved and which things get restored. This one turned out to be we thought it was going to be hard. Variatic operations, however, they support varying numbers of arguments and results, and the multi-adic call results are very hard to express. We do not have a solution. We believe that we will have a solution. This is still work in progress. We certainly are going to need additional passes, and there may need to be some surgery involved. Some issues involved in the internal structure. TableGen turns out not to be suitable for large and irregular ISA. We've got over 1,000 distinct operations times 10 for all of the widths. And our first approach was to use DEFM and the for loops in TableGen, but that got out of hand real fast because the hardware's under development. We're changing the instruction set weekly. And the manual process of changing and verifying the changes of the target were just totally hopeless. The review time was the major problem, not so much the time to write the thing to put into TableGen, but to do the review work to verify that it actually happened. So instead we switched, and we got our own hardware specification to generate the TD files through an XML intermediate. The result is enormous, but a dumb LLVM target. We cannot plug in after instruction selection, but we need the instruction selection facility, but we must exit before the rest of the back end. So we really badly needed hooks after instruction selection, but before registrization. Those didn't exist. We've added them and put them in. We wound up having to refactor the trunk in a number of places, but this broke third-party code. The models in the existing code carry many implicit assumptions, and the backends depend upon those assumptions. This apparently is a recurring problem that others have faced. Naturally enough, given its history, the overall structure is rather ad hoc, entirely to be expected. This is not a complaint, it's an observation. But nonetheless, it's something that we have to deal with, and especially more than the next risk machine that is a target. Cross-basic block optimization is difficult in the back end. We need to do a lot of it. For example, we have conditional call operations, and recognizing that these are applicable turned out to be rather difficult, and particularly because these have results whether or not they are taken, and that is completely alien to the model. We gave up and moved those to the specializer. We expect that there will be some LLVM issues that we haven't gotten to yet. Vector lengths are not known. We need to be able to compute the iteration interval. Software pipelining is a major function for us. We have not attempted to deal with that yet, but we anticipate difficulties. The pipe body is your prologue and epilogue. You don't have that. There are a set of language issues that we really want to actually, when we have it working, and with LLVM, we want to be able to propose things to the language committees. And we need things like saturating exception type builders, or would like to have them. But that requires a type promotion lattice, and you know how what work that will be in the front end. Multi-result calls are a similar issue. Value result arguments, this also is a problem, and again, not supporting by C. To wrap up, I can give you a short progress report. Things actually have gone faster than we expected. There are still a lot of big worries. The code wound up being cleaner than expected, But our first compiler, which we abandoned when we moved are in the process of moving to LLVM, was based on the Edison Design Group front end, which is a gold standard in code quality and internal documentation. And so while the LLVM was cleaner than we expected and a lot cleaner than some other compilers we won't mention, nonetheless, is not up to the standard. The community has been exceptionally friendly. We've gotten help all over from many, many people, and this has indeed been a very warming and worthwhile experience working with the community. The bottom line is we believe that we made the right choice with LLVM. We still think you gotta fix the pointer problem. So far. Now, one last thing. It turns out that our discussions with the communities is that everybody knows that something needs to be done about TableGen, but nobody knows what to do about it. Our observation is that what TableGen is in fact very similar to what our ISA specification does. Rather different way, but very similar. Our specification machinery has been stable for over 6 years. We can add a new operation or attribute in 10 minutes, and everything using the new spec just works. It uses heavily esoteric C++ templates. Has anybody ever written a template taking template arguments that themselves take template arguments? Okay? That's used inside, and there's this marvelous piece of code with 42 consecutive right angle brackets. It works. It works amazingly well. And I'd be more than happy to explain how it works to anybody who's interested in the details. But we make you an offer that while our code is certainly not suitable for importing as is, its purpose is very different. We would be more than happy to supply that code in source so that people can use it as a model to the extent that they might find that our approach might be useful in working on and improving TableGen. If it's of use, we make it available. If you want more information, there you go. The mill is a fascinating machine. It is very different. LLVM has responded surprisingly well, and we're very glad to be involved. Thank you.